Everyone, Mr. Fritz here. We're going to talk about constant velocity problems. And let's begin by taking a look at these points OA. So I've got some object that begins at point A. I want to know what its position vector is. Remember, a position vector is from the origin O to A. So the position is at A, but the position vector is from O to A. So go ahead and draw that in. It should look something like this. And let's just call it vector A for the sake of argument. The next thing I want you to try to do is I want you to think about this object at point A is moving at a constant velocity b. So every second or every interval of time we're moving b units away, or we're moving a vector b away from this point until we hit point R. So what vector would describe this path from A to R? Go ahead and draw that in and see if you match up with what I get. I get this right here. This is AR. Here's my next question. What is the resultant vector? If I move in this OA path and then AR path, draw in the resultant R. It should look something like this. I'm going from O to R, and that's equal to the sum of this vector plus this vector. And the object really will continue to move. It's moving in this velocity, and we can imagine this being a boat or a plane or something like that. We are continuing to move in this constant velocity in this direction. So really R is going to keep changing. And you can maybe even see that this resultant is going to continue to become this longer and longer and longer and different direction R as this vector continue, or as this position, as this particle keeps moving on and on and on. This resultant is going to kind of stretch and move and move and move and move and move. The resultant is going to continue to change, as I said, but in general, if I wanted to find this vector, this resultant vector, it's going to be whatever OA is plus whatever AR is. And this R is going to continue to move as time goes on. Now here's the kicker. AR is equal to T times vector B. I want to let that sink in. This AR vector I can figure out by figuring out how many B's I can fit inside of this AR. Or thinking about the number of seconds, let's say we're talking about time is in seconds. For each second, I'm moving another B in this direction. So this AR will be described as really how many seconds have passed times the number of B vectors being used. So if there were 3 seconds, then there should be 3 B's inside of this AR vector. And if we know that OA, if we call that vector A, and we know that AR equals the time times vector B, we can conclude that the resultant vector, R, in general, is equal to this A times plus the time passed multiplied by the vector B. This is like the general vector velocity equation. So this is really key. So let's see how we can use this velocity in an example. This is a constant velocity problem. I have an object that's initially at this point, and it moves with a velocity vector of 3i minus j. So I'm looking at this right away, and I'm thinking this is the same thing as 3, negative 1. I want to find the position, not position vector, but the position of the object at any time t. In this case, t is in minutes. I want to do all kinds of stuff here. So let's start off with letter A. And in general, R is going to equal I'm sorry, I want to find the position, not the position vector or anything like that. But let's just write down, in general, this vector R resultant is going to equal A plus T times B. And if I want to find the position, let's think a little bit about what we know about the vector equation given in this example. So this xy position vector should be given by my initial position, and the initial position vector is going to be 5, 10, plus times my velocity vector, which is 3, negative 1. And if I take this information, kind of crunch it together, I know that my xy position vector is going to be given as 5 plus 3t and 10 minus t. Basically what I just did is I added these two vectors together. So the position point, the point of my position, the coordinate of my position, is going to be, basically the x will be this, 5 plus 3t, and the y will be this, 10 minus t. So this in general is going to give me position at any time t. Notice this is a position, not a position vector. That's why this is written as a coordinate, not as a vector. So that's A. Let's talk about B. I want to find the position at t equals 3. Well, this is pretty straightforward since I just spent all that work finding the position at any time. So I'm going to take point P will be at 5 plus 3 times the time is 3, comma 10 minus 3. And so the position will be at, what is that, 14, 7. All right, and then finally, the last piece of this is to, let's do another color here. The next piece is to find the time when the object is due east of the origin. So let's think a little bit about this for a second. Kind of graphically what's going on, I've got this object up here at 5:10, about here, and it's moving to the right and down. So it's kind of moving in this direction. Eventually, it's going to cross the x-axis. This is east of the origin. Here's my origin 0, 0, and due east would be right here. So really another way of asking this question is when is the y equal to 0? Because due east would be when my y equals 0. So in order to find that, I just have to look at my y values. And we found the parametric equation y of t is equal to 10 minus t. So I want to know when this equals 0. 0 equals 10 minus t. Do a little bit of algebra. And I find that t equals 10 minutes. That's how long it'll take for me to be due east of this point right here. So why don't you try this example? It's a whole lot like the last one. Pause the video, give this one a shot. All right, so here is the solution to this problem. Constant velocity, pretty straightforward as long as you can handle the vector equations. Let's talk about another type of question you might see. These are called closest distance problems. And I want you to think about this picture. You should have this in your notes. And let's imagine that this describes some ship sailing in the water. This isn't really a mountain. This is like a bird's eye view of what's going on here. So here's the water. Let's put some waves in this, make it look like a real ocean. Ah, yes, this was reminding me of my time in Florida. And then here's land. We might even put a tree in here. Why not? We'll have, or let's put some bushes, right? So here's like a little bush here, and then here's a little bush and we have this land mass, and somebody's looking out from point P, and here's a ship that's going by. It's sailing through point A in the direction of B. So B is like my direction vector of motion, and I'm going in this direction. Here's my port, P. I want to know at what time will the ship R be the closest to the port. So if we're moving in this direction, I want you just to think a little bit. If I continue in this path, at what point in this path am I going to be closest to P? So think about that. Right now, where I begin, I am this far away from P. As I continue to move on and on and on, R is this far away from P. At what point on this line in the direction of travel will I be closest? Think about that. Hopefully what was coming to mind was a perpendicular line. This is the closest I will ever get to point P as long as I'm traveling in this direction. So how do we relate this to vectors? Well, when PR, this PR is perpendicular to this AR, we can talk about the dot product, right? We know how to find perpendicular vectors. If vector PR dot the direction vector of my motion is equal to 0, then the scalar product must be 0. Therefore, these must be perpendicular. So let's keep that in mind. Perpendicularity and dot products equaling 0. So here's a beast of an example. I want to find basically, a few things. I've got this graphic, once again, we're at sea. Here's the land. Something is moving out of sea. And we want to, let's kind of read through this. Measured in distances are measured in kilometers. This ship is at R. It's right here. This is the position at point R. And it is moving in this direction, 3, 4, at a speed of 10 kilometers an hour. Now, one thing I want to point out is this is not my velocity. Right? It says moving in the direction of 3, 4. So that's not my velocity vector. This says it's a speed of 10, so this is going to be the magnitude of my velocity vector. So we're going to kind of have to use those two facts together in just a second. I want to find an expression for the position of the ship, not the position vector, but the position of the ship in terms of t, where t is the number of hours after leaving port A. So we kind of started here and left in this direction. So let's attack letter A first. The general form of my vector equation is going to be r equals A plus time t times the velocity vector b. So right now, for this vector b, this velocity vector, we have a direction and magnitude. So we have to put those things together to figure out what the actual velocity vector is. What do we know? We know that the velocity vector, whatever it is, vx, vy, is going to equal some scalar times that direction vector that was given before, 3, 4. Right? So the velocity is going to be, it's parallel to this direction, 3, 4. I just don't know how much I'm multiplying this 3, 4 by to get my velocity vector. But I do know that the magnitude of my velocity, which is my speed, is equal to, what did I say it was? 10, right? Yeah, 10 kilometers an hour. And that should equal the magnitude of this whole thing, or k times the magnitude of my direction vector, 3, 4. And so this is going to be 10 is going to equal k times the square root of 9 plus 16, which is equal to 25. Square root of 25 is 5. So 10 will equal k times 5. So k must equal 2. How does that help me? Well, if k is 2, then my velocity vector is going to equal vx, vy is going to equal 2 times 3, 4, the vector 3, 4. So my velocity vector is 6, 8. All that work to find my velocity vector. I'm not even done. Really what I've started is I've just found the b in this vector equation. I want to find the position of this thing. So if we keep going forward, let's change up the color here to green. The position at xy is going to be given as, this is like my A, my resultant vector is my position vector xy. A is going to be my initial point. My initial point is -8, 3, as given by this, plus t times my velocity vector, 6, 8, which I just found. So the position at r is going to be, let's smush all this together, my x component is going to be -8 plus 6t, and my y equation, or y component, will be 3 plus 8t. So all of that just to find my position at any time t. So if I said we are 3 hours in, I'm plugging in a 3 to these t's, and I can figure out just exactly how far away I am. So that was A. Let's do B. I want to find the time when the ship is closest to port P. So let's again think about this. When I'm going to be closest when this line is perpendicular to this line. So I want to know when is R here. That's what I'm interested in. I want to know when the vector PR is perpendicular to the direction vector 3, 4. And I find that another way of saying that is I want PR dot 3, 4 to equal 0. So we kind of have to figure out what PR is. So let's recall what the R position is. Or actually, let's write down what the point P is. P is at 10, 2. And R is from the last part of the problem, we had -8 plus 6t, comma, 3 plus 8t. So if I want to find the vector PR, I need to begin at P and go to R. So that means vector PR is going to equal -8 plus 6. This is my vector R. or my position r, excuse me, and then 3 plus 8t. And what I have to do is I have to subtract the point P to find my vector PR. So this is minus 10, and this is minus 2. So this is like my point P. So I took R, subtracted P, to find the vector PR, which is equal to, that'll be negative 18 plus 6t and 1 plus 8t. All right, so that's vector PR. I want this vector PR to dot with 3, 4, and I want it to equal 0. So now I just have an algebra problem here. So I'm going to take, let's squeeze this down here. Negative 18 plus 6t, 1 plus 8t, dot 3, 4 should equal 0. So the dot product will be expressed as 3 times negative 18 plus 6t plus 4 times 1 plus 8t. That should all equal 0. So let's do a little bit of algebra. This is negative 54 plus 18t plus 4 plus 32t equals 0. Let's combine our like terms. This is negative 50 plus, that'll be 50t equals 0. And see, I think I have just enough room to squeeze this out. This is going to turn out to be 50 equals 50t. So t equals 1. What does that mean? 1 hour after leaving point A is when I'm closest to the port P. Whew, that's a lot of work. So make sure that you kind of rewatch this if you need to. But this all kind of hinges on the fact that the dot product of perpendicular vectors is equal to 0. So for one final problem for you to try, a whole bunch of stuff, draw things out, that's going to help you, but this is going to be a lot like the last problem. So pause the video and work through this one, and then resume when you're ready to see the answer. All right, so here's my solution for this you try problem. Hopefully you got something like this, and thanks for watching.